Hello everyone. Um, I would like to quickly ask a question if you can hear me. And super. Okay. And the sound quality is should be fine. Should be fine. Okay. Um, basically, you don't have to write it in public chat. What I will like to do is I will always create polls and you can just vote when the poll appears on your screen, so which is more appropriate answer. And that's how I will know. It is much easier for me to gauge the responses here. Super. Okay, so I welcome you all to the numerical simulations and metal forming course. You should be able to see my screen and my camera, and this is basically a relatively advanced level course, more on the application side and the developmental side, and Professor Ulrich Prahl is responsible for this course. Um, so yeah, Professor Ulrich Prahl is the professor for forming technology. He is also director of Institute of Metal Forming. He is mainly responsible for this course, and Dr. Irani and me, Faisal Qayyum, we are assisting him in delivering the lectures and answering all the questions and basically doing all those sort of things. So Dr. Irani is a postdoc member at our institute, and he is working with numerical simulations for quite a long time. Once he will be starting, he will be delivering a few lectures, and I will be delivering a few others. Once he will start delivering his lectures, probably he will introduce himself in more detail. For now, I will talk about myself. Yeah. So I am Faisal Qayyum. I basically am a mechanical engineer. I did my master's in applied mechanics and design, with specialization in numerical simulations. So I've been working with sheet metals, with thermomechanical simulations for quite some time, specifically about fatigue crack propagation. And since I came to Freiberg in 2017, I have also been working with crystal plasticity simulations as well as other finite element based simulations. So that is something which we would like to incorporate in this lecture. And yeah, move forward. So I feel that we are capable enough in understanding the needs of the students at this stage at the master's level, and also well capable of helping them with obtaining what they really require from this course. So yeah, when we talk about the requirements, let's come towards the lecture objectives. So this is what we would like to cover today. So the objectives of today's lecture are to understand the educational aims of the course, a very important point, the economic importance of metal forming, what is metal forming, and what is numerical simulation. Um, then we specifically want to understand why is metal forming numerical simulation modeling so important, why we have a specific subject about it, and why we are teaching it at a master's level. And then we will talk about how the course is structured and where can and how the course is structured and where can the simulation club help you. You will also get to know about the simulation club, and you will also get to know how this will help you further. And almost around the end, we will talk about how one can get access to the course books, learning material, and course data, and so on and so on. So yeah, I will keep on looking at the public chat. So whenever you have questions, just punch them in. I will look at them and answer them at an appropriate time slot. Um, what I would like to quickly ask is, how many of you have already taken part in the fundamentals of plastic deformation course last semester? So if you have, vote yes. If you haven't, vote no. I would like to know, basically, I would like to gauge an idea about um, you will, so I will know that how many of you know about me, and I will know that how many of you know about the basics or some of the things which we already taught in that course. Because that is the first step, and then we are stepping into this course, and yeah, so I would just like to know my audience on where they are coming from. Okay, interesting. So it's almost 14 people voted, 7 are yes, 7 are no. So I would assume that there's a 50-50 percentage. Some people have already taken part in the fundamentals of plastic deformation course. Some people, some students haven't. Okay, so you then I would also like to ask, are you already familiar with the online learning platform or online learning style? So have you already taken some courses where you were taking online lectures and then going through the assignments and submissions and so on and so on, or you're not? And from here, I would get an idea that should I be explaining more about the methodologies on how you can do it, or it is self-explanatory that when I'm saying you submit it online, you will be able to find the options and you will be able to submit things when possible. Okay, so almost okay. And I'm already seeing that some students are not voting at all. So they are the idols, just there to um, see. I don't know, but some people are just not voting. It's okay. Uh-huh. So I see that unstable internet. I'm sorry. It's okay. You don't have to be sorry. Okay, so I see that some students already know, about half of the students already know about the online learning methodology, and half of the students don't. Again, it's okay. Um, so yeah, then I would explain the last point in the end, with the Opal opened up and so on. So yeah, now let's go to the educational aims of the course. The overall course basically is designed to help students learn the modeling of complete process chains by means of computer algebra systems and finite element programs, taking into account the interaction of material flow and material evolution, industry relevant process chains of forming technology. So that is the educational aim of this course. And to relatively simplify it or to advance it, another important aim of this course this year, because we have revised it more or less, is to help students use the imparted knowledge coupled with appropriate tools and softwares for using it to model and simulate simple forming processes, and use the obtained results to make simple decisions about metal forming processes. So before the start of this semester, there was a debate within our colleagues, and Professor Pral was very consistent about we need to update this course in a way that it is useful for the students, because we see that regarding numerical simulations, although students have passed the course, although they know about the basics, are still unable to do some basic calculations or use the tools and softwares and do some calculations. And therefore, this year around, we have revised it in a way that apart from the theoretical knowledge, they are able to, the students are also able to get their hands-on experience with some of the tools and things, which will in the future come with time, and you will see. So yeah, this is the basically educational aim of our course, to help you with learning the tools and technologies, um, uh, which can assist you with understanding the interaction of material flow and material evolution, industrial relevant processes related to metal forming only. When we talk about metal forming, we need to understand a little bit of the background. So why um, metal forming is so important. and we can easily start it from the recent world crude steel production figures. And we see that if I can use a pen, yes, and we see that it has been consistently rising. And now in 2020, although it was in the peak times of corona, although it was a lot of industry and a lot of trade was affected, still we see there is a slight hike here, and we see that the world crude steel production is standing around 1,878 million tons um, um, per year. And the figures have been taken from the World Steel Organization, which takes care of all these um, um, uh, facts and figures. And yeah, so basically, a lot of crude steel is being produced every year. And if you look at the breakdown, so where is this crude steel being produced? We see that a lot of steel is being produced in Asia. So if you look at this cluster of China, Japan, and India, we see that a lot of steel is being produced here. So the number one, number two, and number three steel producers are all there. And then we see that in Europe, the, the crude steel production is relatively lower, but is quite important. And in the next slides, we will see how. And then the rest of the crude steel production is basically distributed throughout the globe. So this is basically the crude steel production side. And then we see that the how is steel produced and how is versus how the steel is used, and we are specifically talking about the year 2020, and we are taking generally the average value. So we see that a lot of steel is being produced and consumed by China, by India, by European Union, by Asian countries, and then the rest is basically distributed in smaller steps and smaller sections and so on around the globe. Um, then if we look at the steel use per capita, so this here the story is slightly different. So previously we saw that how much global steel is being produced by every country. Now here we can see that which country with respect to its population is consuming a lot of steel. And then here we see basically South Korea has a huge um, um, steel use per capita ratio. China has a huge ratio. Um, then we see that although India is a big producer of steel but has relatively smaller usage, we also see that Germany has quite a large per capita steel usage, more than United States, more than United Kingdoms, um, more than Spain, and so on. And this is probably because and we see that Poland has quite a large per capita steel usage. Sweden has high, and usually this high demand of steel use per capita is associated with the steel being consumed for production of high quality goods. And when we associate these figures with the automobile industry or the aircraft industry, we see a direct correlation. So so a lot of industries related to automobile and aerospace are as they are present in these countries, so they are basically consuming a lot of steel, and the steel demand is going higher. And yeah, so then when we see that, okay, so this is the demographic of how steel is being used, we can also see that how in what fashion the steel is used. And generally, we see that a lot of steel, so almost 50%, 52% is mentioned here, is used in the construction, building and infrastructure. So to construct bridges, roads, buildings, wind turbines, and so on and so on. And then the next big chunk is used in producing uh, mechanical equipments. So almost 16% of it, which means cars, which means rockets, which means aeroplanes, which means um, all the heavy equipment and machinery and cranes and so on and so on. So a lot of a big chunk of that is also used in manufacturing them. And then we see that the automotive sector is specifically mentioned here separately, which consumes a lot of um, steel, and then some is then used in metal products, and then other in transportation, and then domestic appliances, and then a very small amount is used in electrical equipment. But this is not, but this is just the biggest chunk of um, steel um, consumption. Now, when we think about it, and when we think about crude steel production, we see that um, the crude steel is not really directly used as in the form of billets or blocks in all these applications. Um, I would like to ask you about, you can write in the chat on how you think the steel is used mostly. So in what um, form? In the form of a sheet, in the form of a wire, um, or any other form you can think of. How is the steel used in the basic form, which can then be molded into different shapes um, to manufacture these products? Bars, bars and wires, sheets, hmm um, steel bars, and it is also used in the form of sheets. So that is basically the very basic form of how steel is used. But when we talk about the other demographics, so when steel is produced, it is not usually produced in the form of sheets or bars. It is usually produced in the form of big blocks from from molten metal. It is transferred into the big blocks, which are then somehow converted into these um, bars and wires and sheets and um, and other shapes, which are then used in these industries. So yeah, that's right. Um, so we see that converting steel or any metal into desired shape is quite important, is very necessary to keep this economy running. And metal forming is basically a way of shaping metals, any metal, into desired shape by appropriate thermomechanical processing, and that processing is called forming. And if we talk about, so that is a very basic or general definition. And if we talk about a specific bookish definition, we see that the metal forming is um, the process of fashioning metal parts and objects through mechanical deformation. The workpiece is reshaped without adding or removing material, and its mass remains unchanged. Or we can also say that metal forming operates on a material science principle of plastic deformation, where the physical shape of the material is permanently deformed into the desired shape. Hmm. So you generally understand the concept of what is metal forming. And then if we talk about different manufacturing methods here, we see that they can be classified into different types, which is generally primary shaping, which is basically shaping a liquid metal into a solid shape in the form of a die or something. So that is called primary shaping. And then there is a very major chunk of forming operations which can be used to manufacture different materials out of metals. And then there is separating methods, joining methods, coating methods, and um, material properties. I don't know why this is here, but yeah, generally we see that the forming operation can be then classified into compressive forming, into tensile compressive forming, into tensile forming, into bending, and into shear forming. And when we look at their examples, we see that compressive forming is usually when we are applying compressive load on tensile compressing is generally when we are um, applying um, different types of loads at different deformation positions. And then tensile forming is only when we are stretching it, so basically applying tensile load during forming, and bending is of course when we are bending it, and then shear is usually when we are trying to uh, deform it in the shear direction or trying to cut it, which for which separation is basically separately mentioned here. And then you can see different examples of how the metal forming operations are classified. So the classification is quite diverse. It is a wide spectrum of how the load is applied and how the material deforms into a permanent shape. Oh, it does not work. Now, when we talk about metal forming and generally about all the steps in whatever way we want to form a material, um, um, it generally follows a certain path. So the path follows in a way that we have we have data about a billet material, and that goes and that tells us about the flow stress and forgeability of the material. And then we have our ramp velocity or the deformation velocity or the overall um, process through which we are applying force, and that gives us um, two information about the strain rate, so how fast the process will go, and then for how much time the process will go on. And this strain rate is basically important in defining the flow stress or forgeability of the material. And then the third thing which is important for us is basically um, the geometry of the billet, um, the temperatures, and the interface lubrications. So basically, if I say these are all the input parameters which we get from which we get from any process, if we want to draw a sheet or if we want to draw a wire or whatever. So we will know about the what material we have, how fast we want to do it, what are the temperatures, what are the die shapes or thickness or the diameter for which we want to shape it, and then what are the interface conditions. And 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 basically these conditions then give us the temperature distribution during the forging or contact time, pressure, and that basically leads to um, the friction calculation of the friction conditions. um, the flow stress, the material data basically gives us information about metal flow, forging load, and forging energy. And basically this is what we are interested in calculating through any process which we um, carry out. And all these parameters need to be adjusted to get desired mechanical, thermal, and to get mechanical, thermal properties of a specific component, and that is what we are looking for during calculation. So we precisely want to know um, how that goes. So yeah, we always need specific shape and properties associated with the manufactured part. So here, as an example, we will take a case study of a car door. So we know that a car door is basically not only um, useful just to get inside or get out of the car. It is um, it is providing quite useful structural component strength or things like this. So the basic question which I want to ask before I move forward is, which necessary properties should a car door have in order to function properly or in the best way? What do you think? It should have strength. Okay, so what I will do is I will write these things here. Strength should be lightweight. Should be formable. Now, this formability thing is important. So, one person said that it should be formable, the other person said that it should be tough. This formable thing is important, it is interesting. We want the material to be formable when we want to convert it into our desired shape, and then we want it to be strong and non-formable, more or less, when it is installed in the car. So one property is desired at one point, it is then not desired at the other point of the service life. That is tricky. It should have a good impact resistance. Yes. So so it should be tough. It should be strong. Although these are synonyms, depends on which direction we are coming from. What else? I think it should also be uh, um, thermally stable, so it can um, it also be rust proof, so um, um, antioxidant. So sorry, it should also withstand um, what was that? Yeah, so it should also withstand rusting. Um, so and then we see that these are basically um, opposing um, attributes. So we want it to be lightweight, yet we want it to be strong. Um, then we want it to be formable, yet we want it to be tough. Uh, and 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 so there cannot always be a door with which has all the desired attributes, but an optimization of where a sweet spot is for our case. So it should be lightweight enough, yet it should be strong enough. Excess of anything can go very wrong in adding a lot of weight to the automobile, or reducing the service life, or so on and so on. Or specifically when we talk about the life after failure, so when an accident occurs, how it would behave then is completely different from how we require it to behave when it is installed and that it is not going against an it is not going through an accident. And what I have mentioned here is it should be from the it should be corrosion resistant. Yes, it should be isolated, and it should also provide yeah, so we will see it here. So we talked about it should be light, and the important point is it should be inexpensive. So it cannot be a material which is very expensive. Of course there are some materials which are lightweight, which are very high, which are strong, but then they're quite expensive. So we also want a material to be inexpensive. We want the material to be easily manufacturable into the desired shape, yet it should be strong. It should have rust proof, shock proof, which was here somebody mentioned, and then good fatigue strength, because the car basically throughout its life cycle goes through a lot of um, it is not always running on the smooth road, so it is going through a lot of cyclic loads, and we do not want the material to be very bad, to have a very bad fatigue resistance, so it basically cracks and drops whenever, at one point in time. So we want it to have a good fatigue strength. We also want the material to have good joinability, so we can manufacture it whenever, by welding it or joining it with different components. It should be conductive, because now a lot of electronics is dealing with the conduction of electricity through the car body, and with that we are running some sensors, we are running some switches and signals, and so on and so on, and of course some um, uh, non-conductive equipments like fiberglass or carbon fiber, or so on and so on. So basically, when I talk about glass fiber, it is basically um, epoxy reinforced glass fiber, so epoxy reinforced carbon fiber. So they provide most of these attributes but are not always conductive, and then a few more depending on where, for which car the door is being produced. um, and when we talk about this, we see that we require a lot from just a car door, and that is the reality of everything which is around us. So if you look at anything made of metal, almost all this list will fit perfectly for anything. So we require basically a material to have a lot of attributes and properties for a useful application. And um, I will just erase it. And how do we know before manufacturing a car that the desired objectives will be achieved after a certain set of processes? One way of doing it, a conventional way of doing it, is by doing a lot of experiments, by manufacturing a lot of car doors and looking at the possibilities of which one fulfills the requirements more appropriately, and then using directly that one. And now a relatively advanced form is by using numerical simulations, because when we know about the materials, we know about their behavior and methodology, and what will happen if we do an experiment. We can combine all these numerical models, um, intelligently compute an appropriate optimal solution, and get our desired results. So we are trying to predict the future, basically. That's what we are intending now. That was a very crude introduction of what numerical simulation is. And if we talk about the specific definitions, um, initially a very general one, um, it is to use mathematical tools and principles to predict the future or enhance knowledge about the existing phenomena. Of course, with its own limitations and assumptions, falls under the category of numerical simulations. And if we talk about the bookish definition, we see that the definition of numerical simulation is related to process of mathematical modeling performed on a computer which is designed to predict the behavior of an outcome of real world or physical system. It can be used to explore or gain new insight into new technology and to estimate the performance of systems too complex to model with simple mathematical equations. And the important point here is that when we are studying numerical simulations, it is very important to have background knowledge about the following subjects. So you should already have a basic background about the applied mathematics, about the integrals, about the derivatives, about the Fourier transformations, and how we solve complex equations and find absolute solutions or approximate solutions, and systems and methods like this. And um, and yeah. generally about absolute solutions and approximate solutions. We also should have a basic background about material science on what metals or materials generally are made of. They're made of atoms or electrons and protons and neutrons and so on and so on, and how they come together and form material world around us, and then how do those materials based on their intrinsic attributes behave, how they deform and things like this. And then as we talked about a question about the fundamentals of plastic deformation is the theory specifically about how the materials are permanently deformed into any specific shape. What are the basics, what are the backgrounds, what are the laws and principles with other scientists or researchers in the past have devised, and how they can be used to estimate some values. And then basic computer literacy on what is Windows, what is a mouse and a keyboard, how do we install certain things, how do we uninstall certain things, and how does a computer write a data set, how to read that data set, how to interpret that into a useful language, what is an input, what is processing, and what is an output, and specifically things like this. And what I would mean by computer literacy, also very important, is how to Google appropriate information and how to find appropriate answers on YouTube, because this basically is what computer literacy is more or less nowadays all about. So you don't have to know anything, but the whole um, sea of knowledge is on your fingertips, um, based on your approach. On if you know how to find something, you can easily do that. So by computer literacy, we mean this. So when we are wanting to know more about numerical simulations, this is basically the background which you should at least have. And then I would come to this very nice quick touch of the building blocks of um, a numerical simulation model. So as we talked, so generally there is this input, and then there is this processing, and then we get the output. And while doing this, we have some constraints on what can be done and what cannot be done. So when we for for to ask a computer to solve a problem, we need to tell the computer everything. Um, no, do that. Um, I usually talk about a very simple and easy example here, and what I usually during discussions it really helps is to just touch a little bit of the fundamentals. So from our primary science, we know that atoms are the smallest building blocks of any material in the world, and they can be divided into subatomic particles like electrons, protons, neutrons, and then now we know that these electron, protons, and neutrons are also not the fundamental particles. So there are quarks, and there are different types of quarks which come together to form these particles. And then these quarks are not only the building blocks, so we also know that there are other particles. For example, there was a very recent discovery about the Higgs boson particle, which basically gives weight or mass to the components, we say. And then there is a very quantum in the quantum physics, there is a very competing theory of quantum fields. So we say that all these particles basically are not really the particles, but are just the fields which are interplaying with each other, and in response to that, the particles come out. And then we have a basic problem of where the gravity is coming from, where the time is coming from, and so on and so on. And these are all the fundamental questions of the physics which is going around us, and we still do not know the answers to them. So we still do not basically precisely know um, what the truth is or where the actual science is lying. Yet, if we have a steel bar and we try to bend it, it will just bend and deform into its shape. And so So the bar does not need to know all that quantum physics or the fields or what the truth is. It will just behave intrinsically what it is meant to do. But us as humans or computers and calculators need to know all this information to actually precisely predict what will happen if we apply a load on the bar. So these are two different things. So generally, what we have done until now is we have seen if we apply a load like this on a material, it will behave like this, and empirically modeled it. And using those methods and tools, we try to model it more precisely or in more detail, and that's all what we have done. So we do not, as we do not know how the fundamental physics and material science on a very small scale is behaving, we cannot tell anyone about that because we don't know it ourselves yet. um, it is interesting that we can still do certain things, try and experiment with different things, observe different things, and can empirically model them, or we say that fundamentally, but generally empirically model them in a way that the computer can predict what will happen. And this is what we are trying to do here. So in the computers, we are trying to define, we are trying to tell the computer all that we know so it can predict all that it can with that data and information. So we generally, as an input, we give geometric parameters, which basically talk about the workpiece, which is basically our material which we want to deform, and the tool geometry which will be used to deform that material. Then we also give input of the process parameters, which we talked about. So this is die and tool motion, temperature, lubrication, and which material we have. So how does it behave under different loading conditions? And then, for example, the material parameters are specifically mentioned specifically here. So we talk about how the material is work hardening, what is the strain rate sensitivity, if there is any, the material is isotropic or anisotropic, and how does the temperature affect the material attributes. And there are many other parameters, but this is just a very simple system. So we give input of all these attributes as well as we talk about the constraints. So forming limits. So until what condition the material can deform, and after that it will not deform or it will fail. Um, um, what is the friction coefficient, or so on and so on, and what are the capacity limitations if we really need to give this information. But we will generally, in the constraints, we will talk about that this size or this side of the die is fixed, it is non-deformable or it is deformable, and this side will remain like here, and then so general constraints about the shapes, about the physics behind the system. So we also define these, and then what the system does is basically based on the input model, it takes up all this data, plugs it into the design, plugs it into the equations of loads, energy, stresses, strains, temperatures, material flow, and so on. So it will basically, based on those laws and principles, it will calculate all these attributes and will write it in an output file where we can then see the global responses, see the local responses of the material, and generally get the desired information which we need from that process. So how will it behave, where the stresses where the stresses will be highest, where they will be lowest, how will it deform, what will deform first and what will deform later, and so on and so on. So these are basically generally the building blocks of the numerical simulation of numerical simulation system, whatever it is, whatever it is. Now, considering how drastically the landscape of numerical simulations in the materials engineering and material forming has changed in the recent past, and why? Because there has been an exponential growth in the computing power, and based on that, the dependence on the numerical simulations, or the type of models we are now capable to, or the type of equations, or the number of equations we are now able to compute or calculate within a small fraction of time has immensely increased. So, therefore, the landscape of numerical simulations in the recent past has also significantly increased, has changed, and And to consider that, the course has been revised to teach updated knowledge as well as bring students closer to ongoing practice and familiarize them with some tools. Closer to ongoing, yeah, and familiarize them with some tools. So that is why we have also tried to change the landscape of this course a bit. And um, how we have done that. For example, here we are today in the introductory lecture. So every Thursday from 2 to 3:30 p.m. for 90 minutes we will have um, this lecture on numerical simulations in metal forming, and you will get this course outline in these slides which you can follow. And what we have done here is we have mentioned all the dates and we have shown that how we will go through um, the topics one by one to fulfill the objectives of the course, um, and also keep it in touch and associated with the recent advancements. Um, so yeah, so for example, today the lecture is only about the introduction into metal forming and their numerical simulations, and then in the next lecture we will talk about fundamentals of numerical simulation and metal forming. Then Dr. Irani will take over and will tell more about the numerical simulation methods and terminologies, the structures of numerical solvers and metal forming simulations, and mathematical models of flow curves. And then we will start using those building blocks to construct some interesting realistic applications. For example, initially we will talk about the simulations of rolling process, where we will talk about the theory and where all the numerics is coming from, and then in another lecture we will take in a practical example or a specific example of a case where we will make a numerical simulation model and see what we learned correlates with what a computer can do, or what we can get out of it. Then we will see another similar example of wire drawing, and then we will see another example of forging process and sheet metal process. In the meantime, now as crystal plasticity models are becoming more and more popular, we will also have one lecture about crystal plasticity and how we can use that to do multi-scale modeling. Later you will know why. And in the end, we will finish with the relative more advanced side of artificial neural networks, where a computer basically runs a lot of or calculations to know its limits, and then makes up a neural network which it can use to make quick decisions rather than doing calculations over and over again. So that would be our um, outline. From here onwards, from this lecture onwards, generally you will see that we have one theory lecture and one case study lecture, one theory lecture and one case study lecture, and they have been specifically placed here um, to not only just talk about the formulas and equations, but also talk about how they are used to do some calculations and what are the useful results which you can find out of them. There's a question: are we going to use any simulation software for this case study? Yeah, that is what I was coming towards. So for different case studies, we might use different tools which are more appropriate for these kind of case studies. But generally, the idea is that we will be using Abacus because it is a commercial finite element based tool, and yeah, we have already built some examples which we would like to share with you, but maybe we will also use some other tool. And with that, I come to this next point of Introduction to Simulations Club at Institute of Metal Forming. So based on the interest of the students, one of our previous students basically started with a volunteer group to get hands-on training with finite element simulations using Abacus. And Abacus, you might not know, you might know, is a well-known commercial FEM modeling and simulation tool. I would like to ask a question here. Have Do you know about Abacus before? So have you heard the name or seen it working somewhere or anything? Hmm. Hmm. So seven students said no, six said yes. Okay, and have you heard about ANSYS before? Uh-huh. Interesting. So I see that more students have heard. Probably there would be multiple who would have heard about both, but I see that there are relatively more students who have listened or known about ANSYS a little bit more than Abacus. So just to give you an idea, both ANSYS and Abacus are very competing commercial finite element tools. I think ANSYS is slightly older, so it gives it an edge about the pioneering tools where everything was working. But Abacus is relatively new, so um, it came with some add-ons and fulfilled some of the discrepancies which were in ANSYS. Um, I have personally been using Abacus quite a lot, and therefore know very little about ANSYS, but I generally know that the solver for ANSYS is more um, better to do some fluid dynamic simulations, and the solver to of Abacus and the type of models and equations and methodologies which are built in Abacus are more accurate and more detailed, um, to give better outputs for structural simulations and applications. But of course, generally all the simulations, they both are really nice tools and can do most of the work. So what we have done is we have set up a, simulation club at EMF, and you can see Mr. Farachi here. Oh, he is basically leading that group, and the idea is that the student version of Abacus software is available for free, so you can download that, and then he is basically going online for 1 hour, 1 hour 30 minutes, um, for basically discussion about how to do certain simulations and how to do certain things in Abacus. And what we want to do is we want to give an opportunity to everyone who to participate in it and yeah, learn. So it is an online thing, and probably now a few lectures or would be available online. But yeah, um, um, you can use this. Um, what um, what he does is basically he is breaking it down into its smaller components. So it will start with introduction and basics about part design. Then he will move to different sections in Abacus, and then he will talk about simple drawing processes. Um, then he will talk about simple deep drawing processes, um, rolling, and forging processes. And also, it is important to mention that it is a voluntary group. So it is not compulsory for this course to participate in it, but of course you can get more out of this course if you do take part in this course. And for that, you can note down this information and contact Mr. Farachi, and can get and you can get started with um, learning the basics and so on. And once you will reach this goal here, then we will see what we can do, because then basically you will be able to understand how the basics are working and how to define certain things and analyze certain data and results. Of course, then we have several ongoing projects and ideas at our institute which we would like you to um, help us with. So yeah, that would be interesting. And now, apart from that, these are some interesting books and research papers, not really research papers, but books, which I would suggest that we use as course help books. And the interesting ones, the, from from the priority list is from top to bottom: theories, methods, and numerical technology of sheet metal, cold and hot forming, analysis, simulation, and engineering applications. Um, and then we also want to look at the multi-scale modeling in sheet metal forming, crystal plasticity, finite element simulations, and then fundamentals of finite element analysis. And you will see that most of these books are post 2010. Yeah, so quite new. And because of their relative recent publication, what they do is basically they are taking care of all the previous knowledge and also are providing more adequate, more advanced new information. Of course, this is not the only list. You can yeah go through whatever book you want, again through any blog or link on Google, through any video, to understand the concepts and basics of what we are studying here. um, the teaching material will be accessible on Opal portal. And to show, so you already are on Opal portal. And um, and you can see here, so you already have um, registered here. It is in German, so you've already registered here. And then this is the info page, which you will see that the recorded video. So I'm recording this video, which we will sure upload it here. You will be able to get it. And then basically what I will be doing is I will be adding more data information into the lecture scripts, and maybe there will be more folders here with extra data, with data regarding your assignments or homework, or with data related to other attributes, and then some presentations, and then video lectures, or so on and so on. But yeah, so all the data available here in this folder, or maybe um, a few subfolders. So this is basically about Opal. And then you can, if you can register here, and then you can um, go to the classroom here, and so on and so on. So yeah, if you have any specific questions on how to do that, we can entertain them now, or we can also entertain them later at any point. The assignments activities will be carried out using Opal portal. So on Opal portal, there are possibilities of giving in short assignments and giving in certain um, um, questions or surveys or links or things like this, which you will always take part in. So we will announce them in advance. You will have to participate in them by a certain deadline, and yeah, then they will be marked. And recorded lectures will be available on YouTube, or um, what portal was that? Or on Video TU Fabric website. You can get the link from this Opal portal. Um, now we can talk about the exam grades and learning objectives. So the learning objective of this course is this one, which we have already mentioned, but here I've just mentioned it again to um, revise. So modeling of complete process chains by means of computer algebra systems and FE programs, taking into account the interaction of material flow, material evolution, and industrial relevant process chains of forming technologies. Um, so I'm still not sure if the exam will be online or in the presence. Um, Generally, the exam is descriptive, is the descriptive exam, and it is a pen and paper type exam. The exam of this course is to check if the student has fulfilled the learning objectives again. We want to check this. And hands-on experience with simulation tools will not be part of the exam. So when I say that take part in the in the simulation club and learn the tool and see how things are going, so that is not something which will be the part of the exam, but is just a volunteer activity which will help you get most out of this knowledge. So yeah, now I would like to um, start with this short video, and um, can you listen to the audio? Super. Cool. So yeah, I could not find a really nice video about structural simulations. So this was specifically about the fluid dynamic simulations around an aeroplane, but similar simulations are also also carried out for the structural applications of the aeroplanes and all other structures. For example, there we are not really interested in the pressure, density, and um, temperature of the gas molecules, but we are interested in the deformation, in the stress, and yeah, and the deformation and the stress of the elements and other attributes if we are interested. So how does an applied force or a g force will affect the structural integrity of a component? Um, So yeah, from the video as well, you will know and you will be able to make map of how important this piece is and how well it can be integrated with all other applications around. Is that numerical simulations are being adopted by more and more industries for fast, cost-effective, optimal, and accurate development of an engineering components. They are being used for specifically, I would say, um, high risk factors. So when we talk about rockets and aircrafts and automobiles and heavy equipment, we also talk about unique projects. So the world's tallest building, the longest bridge, or things like this. So they are basically we want to build them once, and we want to build them correctly. There is no margin of error there, and we want our all our investments to be safe, and we the people around them to be safe and everything, and numerical simulations play a huge role in assuring that. So therefore, with the advancement of computers, the numerical simulations are being adopted by more and more industries for fast, so we get the answers quickly. Experiments and preparing samples and doing tests takes time, is cost effective. We only need a computer, appropriate tools, and more or less it can solve the issue. Um, we need optimal solutions, as we discussed about the car door. So we need ductility and strength at the same time, yet they are two opposing factors. So we want to get an optimal point of where both are in our desired range, and then we want to have accurate solutions. So something which we only do once and still works for engineering components. The complexity of numerical simulations is also drastically increased in the last decade with the advancement of computing power. So as the computing power advanced, we wanted to get more and more information, more accurate and more detailed information. We wanted to solve more bigger and more challenging issues. And yeah, so the numerical simulations became more and more complex. So in general, the simulation tools have become fundamental for engineers in decision-making process, and therefore pose a huge opportunity pool. So now when you when you look at these tools and equipment, so their application and their requirements, you see that for an engineer to make a decision now, it is more important now than any time in the past is more important for an engineer to know about these tools and processes, so he can do his work fast, more accurately, um, and cost effectively to get to the desired decisions rather than solving equations or doing tests. If an engineer knows this and is using these kind of tools to make decisions, um, will do the work done more effectively and in less money, and yeah, more profits. And therefore this skill poses a huge opportunity pool for someone who is good with these tools. So if somebody knows them, there is a huge job market out there which they can work in. On the other side, a huge threat for someone who is not familiar with this technology at all. So in by hook or by crook, you will, as an engineer, you will always come across these tools because the problems have become immensely complex. It is extremely difficult to make all these decisions just based on experiments. So by hook or by crook, this way or that way, you will always come across these kind of tools which you will have to use to make these. You will have to rely on to make these kind of decisions. And if you are afraid of them, you're not familiar with them, you're not very good with them, it poses a huge threat to the engineers who belong to this field. And so there lies an opportunity and a threat in the same skill. And this course is just an insight into the vast pool of engineering numerical simulations. So here we will only discuss the basic fundamentals or the basic or a few examples of how numerical simulations are used in metal forming industry, and not all the examples, not the complicated ones, just the simple ones. But of course, this is just the beginning, and then this knowledge can be used to do a lot, and to do and learn a lot more. And with this, I would say that let's start this journey of lifetime together, because in any ways you will come across the numerical simulation tools. Um, um, with this, I would like to conclude our today's lecture with this last slide. So I would want you to work on some of the things independently. I would like you to brush up your previous knowledge about numerical simulation tools and methodologies. If you have background, probably you have background about materials and fundamentals of plastic deformation, and if you are a mechanical engineer or a materials engineer, you would already know about these things. And then what are the equations and how they're used, and somehow, some somewhere in time, most of us have studied a course related to numerical simulations in the past. And here I would just like to make a quick poll about if you have, so say yes or vote yes if you have somewhere in time before studied simulations, so numerical simulations course. Okay. And if your answer is no, I would like to know about what was your background. So, what was your majors and your bachelor's on the basis of which you are admitted in this course? So, just to have an idea about, maybe you have not studied specifically this course, but maybe something related to it. Just to have an idea on, if not this, then what did you study, which was remotely associated to something like this. Um, while you're answering this question, I would like to say that, yeah, just brush up your previous knowledge about numerical simulations, tools, and methodologies. This will help you connect your previous knowledge with this one a bit better. Um, Skim through the course data which will be uploaded on the portal. So I would like to upload the books, the lecture slides, and the World Steel Association facts and figures online, and I would want you to just quickly skim through them so you are on the same page when we meet again. And again, I would suggest you to watch some YouTube videos and read some articles about how numerical simulations are helping to engineer better products fast. And once you have done that, I would want you to make a rough list of fields in which numerical simulations play a key role to push the frontiers of science forward. And a very interesting application which I recently came across was in forensics. So for chasing um, criminals in the past, you had to what you had to do was you had to have a DNA sample from the site of the crime, and you also had to have a DNA sample of a potential criminal, or a person, or a suspect, and then you would match both samples, and then you would know, okay, so he or she committed this crime. But now, with the help of the simulation tools and with the help of computers, now it is not required anymore. So based on the big data sets, so many firms which take your DNA to tell you about your inheritance, or to tell you about the background which genes are in your DNA. Now they are sharing, some of the companies are sharing data if with the criminal department in USA, and what they do is if any of your um, relatives is giving in the DNA, they can run all the calculations. They can really calculate which gene small sequence is matching, and they can directly link up the person. So they can basically, with one DNA sample, they can predict they can predict from where this person is coming from, so they can build the whole chain. And again, with how the gene of this person will propagate in the future. So the people who have not given their DNA in the future, the children or the children or the children of those, their database is already there. So if even they will commit a crime someday, the criminal department will precisely know, um, just by picking up the DNA sample from the place of the crime, that who should it match it with, and so on. So yeah, this was one of a very diverse. Usually, as mechanical engineers, we do not talk about these kind of applications, but yeah, numerical simulations play a very key role in pushing the frontiers of science forward in all different applications. So I would want you to just go through it and make a list of list of fields and applications in which numerical simulations are playing a key role in pushing the frontiers forward. And with this, my lecture is over. Thank you so much for listening. If you have any questions, you can write them in the public chat. I am open to answer them. If you don't have any, you can leave. Thank you so much. I would upload this recording on the portal, and so on. We will continue. Mm, Muhammad Yasser asked, I am interested to study this course. Unfortunately, I am not well aware of it. So could you recommend some books or literature work so I can study it? Yeah, sure. So that's what I showed in the slides. I will share the slides online, and you will be able to see um, the books and the study courses.